Welcome back, ladies and gentlemen. We're on question 17 from our practice final exam. If f of x is continuous on the interval a to b, where a is less than b, then the function g of x, which looks like x is a variable here, endpoint here is fixed, and then we're integrating in terms of s. We've got s squared plus f of s all squared. Okay, and then what are the conclusions here? Continuous but not differentiable on the closed interval, differentiable but not continuous on the closed interval, continuous, differentiable, and decreasing on the closed interval, continuous, differentiable, and increasing on the closed interval here. Okay. So, what can we do? Well, okay. S squared and f of s all squared. This is definitely still a continuous function, so we can integrate a continuous function. Yes, so, and this is always greater than or equal to 0, because it's a sum of squares. Now, there's no guarantee that f itself is not just 0, and I'm hesitant to say that this is necessarily going to be sort of an increasing... Oh, also, this is not the usual function that we would expect for the fundamental theorem of calculus, part 1. Right, we do need a continuous function, and this is continuous, but we usually have a up to x rather than x up to b, so I'm going to rewrite g of x as negative, and then we'll go to b to x. Alright, is this... So the derivative of g prime is minus, and then that inside function, so x squared plus f of x squared. Well, those are both squares. Squares are non-negative. So if you put a minus sign in front of them, g prime is always going to be less than or equal to 0. So it's continuous, differentiable, and decreasing on this particular range of values here. Okay. Now here's where I get worried. So, less than 0 is definitely decreasing, but less than or equal to 0, well, no, that's not the condition for decreasing. You have to be less than 0. Also, they keep using closed intervals here, whereas if we remember our fundamental theorem of calculus part 1 accurately, we will remember that you actually have to be... You are continuous on the closed interval, but you're only guaranteed to be differentiable from a to b. So any of these examples that say differentiable on the closed interval should not count. A is continuous on a to b, but not differentiable on a to b. It's not differentiable at these closed endpoints, not guaranteed to do that. So I'm gonna say the answer is A, although I personally think this is not a particularly nice question. I'm gonna go with the strict definitions we learned in class, but I honestly don't remember what the answer we were expecting for this one was, because I mean there's a lot of information going on here, and if one of the we like grad students teach sometimes. If a grad student made this question, they might be forgetting some of the subtleties. So I'm gonna say the answer is A, but I'm sure people are willing to complain about that. All right, let's move on to happier questions. 18. If the derivative of the function f is f prime of x is equal to x plus 2 to the 7, x minus 4 to the 4, and x cubed, then f is decreasing on the interval. All right. So how are we going to do this? Well, we could make a nice fancy little chart. We've got the roots of -2, 0, and 4, and so we want the x values greater than 4, x values between 0 and 4, x values between 0 and negative 2, and the x values before 2. And again, decreasing, just as in the last question, we're looking for things specifically negative. So let's take a look at, x plus 2 to the 7. X plus 2, when x is less than negative 2, will be negative. And a negative number to the power of 7 should be negative. However, as soon as we plug in something like minus 1 plus 2 is 1, and that's going to end up being positive. It's going to be positive for the rest of this. How about x to the 3? Well, x being less than negative 2 is negative, and negative cubed is negative. X being less than 0, still negative, but once x is greater than 0, x cubed is greater than 0 as well. And with x minus 4 to the 4, well, no matter what we plug in, except for this root, powers of 4, just like squares, are always non-negative. Okay? So negative times a negative times a positive is positive. So so f prime here is positive, negative, positive, and positive. So just between negative 2 and 0. So our answer is going to be B. All right. 19. How many inflection points does the function x squared minus 2 ln x have? Well, inflection points, we need derivatives. Specifically, the second derivative. Okay, there we go. So we get 2 plus 2 over x squared. So when is this equal to 0? Well, if you multiply by x squared on both sides, and I suppose divide by 2, you have to say, well, what square can I make equal to negative 1? And that never happens. So our answer is going to be none. For no values does this have inflection points. In fact, it's always concave up. Alright, and the last question, at least for this video. How many critical numbers does the function f of x, this little polynomial, have on the interval 0 to 1? Okay, remember critical numbers where your derivative is defined and equal to 0 or just undefined. Now this is a polynomial. Polynomials always have derivatives of polynomials. It's one of the wonderful things about them. So we're probably just going to be solving for the roots of a polynomial. So 6x squared plus 6x minus 36. Take out a factor of 6 there. And we could use the quadratic formula if we want to, or we could try and factor this. So it'll be plus 3 minus 2. And this only has roots, and therefore critical numbers at negative 3 or 2, and so none of them are in this particular range. So there we go. Alright, we'll be starting the next set of questions with question number 21. I will see you for that in the next video.